Hello everybody, my name is David. Uh, Last month I did a 101 sequence detector using a shift register, and I mentioned that there were a couple different ways you could do it. You could use D flip-flops or a state machine also. I'm going to show you the D flip-flop method in this one. So here we go. First off, this is the D flip-flop module in Verilog. We got a clock for input, reset, the data in, and the Q out. Here's the logic: pause edge clock or neg edge reset. If not reset, then Q will be 0. Else, at the pause edge clock, Q becomes D. Now we'll go to the sequence detector. We have the clock, reset, the data in, and the detected signal. We will instantiate the three of the D flip-flops. I got DA, DB, and DC, and we'll create a couple of wires to connect in between them. So the output of D flip-flop A becomes the data input to flip-flop B. The data that comes into this module itself goes into the first flip-flop. Then this one goes into this one. Then the output from this one goes to the input of this one, and then we have an output here. And for the detected signal, we just use an assign statement. So essentially when this is 1, this is 0 because it's not, and then this is 1. So 1, 0, 1. Here's the test bench for it. Got our registers for our inputs, wire for the output, an integer using a for loop down here. Here's instantiating the device under test. We got the same names. Here's a register, a 16-bit register. I just filled with some arbitrary values, making sure I have some sequences of 1, 0, 1 in here, and I got like 5. Here's I create the clock. So this is a clock of 4 simulation ticks of the period. So every 2 ticks, we change it. We'll initialize those registers. We'll initialize it to reset. Initialize other values. Then right before a pause edge clock, we will release reset, and we will start the for loop. So we'll start I at 0, and while it's less than 16, because we have 16 bits, we'll increment it, and then the data input to the seqreg module is an index of the data reg. So we'll start off at 0 here, so 0, 1, 2, 3, and we'll go on from there, and then we'll finish. I already ran the simulation, and here it is. Change the clock, or change the colors this time. So the clock here is white, reset is yellow, the data in is blue, and our detected signal is green. So you can see right here where data is 1, 0, 1, and the pause edge of that clock, when it's latched into the D flop, then we get our detected signal out. Here we have another 1, 0, 1, so we get a detected. Here's another 1, 0, 1 detected, 1, 0, 1 detected, 1, 0, 0, 1, 0, 1, and another detected signal. So you can see it's working. So I'll take you back to this code. You can check out earlier in the video to get the D flip-flop, and thanks for watching.